So, instantaneous rates of change are important. Under another name, we're going to be spending much of this session studying them. Um, Finding them directly from the limit definition is often challenging. It's often functionally impossible. Um, Although the really difficult ones are probably the trig functions that we don't learn about in this class. Even so, we're just going to do a few examples of this, and then we'll move on and we'll learn other ways of finding instantaneous rates of change. We're not going to spend the entire rest of the semester doing this. So my handwriting goes slightly to pot when I have to use the whiteboard, but my normal work area is not available to me. Someone got there first, so please bear with me. So let's find the instantaneous rate of change of this function. And at the moment, we're talking about, we're sort of trying to have our cake and eat it too. We're talking about the instantaneous rates of change at specific values, at 2, at 5, at -7. But instead of giving you a specific value, 2 or 5 or -7, I'm giving you some arbitrary or some unknown value x sub 0. So we're going to take a limit. I guess really, rather than my handwriting going to pot, the problem is that to be legible, I need to write so big it takes up half the screen, and I don't have a lot of room to write. So we're taking a limit. Let's ignore the limit part just for a moment. And let's figure out what this is. So f of x sub 0 plus h, here's the function. X sub 0 plus h squared plus 2 x sub 0 plus h minus 1. So that's f of x sub 0 plus h. That's this. Minus f of x sub 0. Was that a plus? Nope, a minus 1. That's correct. Minus f of x sub 0. X sub 0 squared plus 2 x sub 0 minus 1. And this whole thing is being divided by h. And we're taking the limit as h approaches 0 of all of this. And before we do anything else, what we have up top in this fraction is a polynomial. What we have in the bottom is a polynomial. Well, this is a rational function. So to take the limit of a rational function, we ideally would be able to just take that 0 and plug it right in. And I mean, the problem, as you can, I mean, the numerator, maybe it's not immediately obvious what happens if you just let h be 0, but the denominator is just h. I mean, clearly you get the division by 0 error. So just plugging 0 in doesn't work. So let's state a goal. Um, Textbooks don't always do this, or introductory videos don't always do this. Sometimes people just sort of start hitting the algebra right away. But it's pointless to do algebra if you don't have some kind of goal in mind. Our goal will be to simplify until there's no h in the denominator. Because the h in the denominator is the problem. It's giving you a division by 0 error. If you could get rid of it, we could just use continuity and stick the 0 right in there. So how can we get rid of something in a fraction? Well, the sort of standard way would be cancellation. If we could rewrite the fraction so that it looks like this, we could cancel that h. So that's what we're going to try to do. And the numerator is just a mess. I'm gesturing at it with my hand as if you can see what I'm pointing at. But we've got this thing, this factored thing. We've got distribution that we can do. We're subtracting a quantity. There's a lot of simplification we can try to do in the numerator. And I'll just take this piece by piece. Let's FOIL that out. X sub 0 squared plus 2 times x sub 0 times h plus h squared plus 2 times x sub 0 plus 2 times h minus 1. That was that. Minus 1. Minus, and now this negative sign, of course, distributes over everything. So minus x sub 0 squared minus 2 times x sub 0, then minus 1 plus 1, all divided by h. Okay, pretty clearly, this is not a long-term solution. I apologize for the state of this whiteboard. And I don't have space to write it, but we're still taking the limit as h approaches 0. And now, if we look up in the numerator, some stuff cancels. We've got a positive x sub 0 squared, and we've got a negative x sub 0 squared. Those go away. We've got 2 times x sub 0. and minus 2 times x sub 0. We've got minus 1 and positive 1. And now the limit as h approaches 0. And notice that everything left in the numerator has an h in it. 2 x sub 0 h, h squared, 2h. And I already told you back when I was trying to sort of explain our goal in doing all this, I already told you what I was expecting to happen, which was that I was hoping to be able to cancel an h. And we can pull an h out in the top. H times 2x sub 0 plus h plus 2 all divided by h. And now, remember, maybe before I do this, remember our goal is to get rid of the h in the denominator. If we didn't have an h in the denominator, we could just use continuity and plug 0 right in. So our goal from the start was to get rid of that h in the denominator. And now you see we can cancel and accomplish that goal. So we've got the limit as h approaches 0 of 2x0 plus h plus 2. And everything here is continuous. So because of continuity, we can just take that 0 and plug it in. We no longer have a division by 0 error. And we get 2x sub 0 plus 2. So now if I want to know the instantaneous rate of change at, let's say, x sub 0 equals 3, well, 2 times 3 is 6, plus 2 is 8. Sorry for that very bad notation. And if we want to know the instantaneous rate of change at -2, well, 2 times -2 is -4, plus 2 is -2. And looking ahead a bit, we basically have a function here, right? I mean, if we think of this as an input, this 3 as an input, it's being assigned to 8 as an output. If we think of -2 as an input, it's being assigned to -2 as an output, and so on. So the instantaneous rate of change seems like maybe we could use it to define a function, which is exactly what we're going to do at the start of the next chapter.